Welcome, everyone. This is the Saturday night class, April the 27th, 2024, Saturday night class of Promethean Action. And tonight we'll be discussing the third class of Lyndon LaRouche's class on physical economy. I'm joined by Tony Pappert, and I guess the first thing we should be discussing is why are we studying LaRouche's concepts of physical economy? Most of you are probably not going to become Secretary of the Treasury, maybe one or two, but probably not most of you. The importance is that LaRouche developed a way to figure out what is true and what has value. How do you know what you should do? How do you know what the country should do? What the world should do? In particular, you don't want to be stuck between choosing bad choices given you by the empire, Republican or Democrat, Israel or Palestine, India or Pakistan, et cetera, et cetera. You have to think from a standpoint above that, from the standpoint of what Henry Carey called the harmony of interests. And you don't want to wake up some morning when you're 80 years old and realize that you've wasted your life. You need to know when you're 10 or 12 the kinds of thing that you should be doing, or where you should be heading. So in this third part of LaRouche's class, we will be talking about the difference between action and work. Not all action accomplishes work. Think of all the electricians and linemen involved in building wind and solar farms. A waste of effort with net zero work accomplished. That's the real net zero. Today, more and more people are coming to realize that America has been heading in a suicidal direction. But 40 years ago, when LaRouche made this presentation, most people were generally happy about most aspects of the society and economy. The collapse in living standards was covered up by people having more jobs per household, so they seemed to be surviving even though more people were working more jobs per household. And a bubble was building up on the stock market. And Lind was working to make his insights intelligible to those who could not see the problems. And there were plenty who did, but the majority of people didn't see the problems or tried to ignore the problems. But ironically, today, some of what he was discussing then seems obvious. So people ask us, well, why is he making it so complicated? He's not. He's just being rigorous in his explication. His standard is extremely rigorous. The increase of potential relative population density is the only standard for judgment. The increase of potential relative population density is the only standard for judgment. That is the standard that you have to apply to everything. And that's why LaRouche's physical economy is the king of the sciences. So in this third part of LaRouche's class, he's attacking the denial of the negentropic creative nature of man. And not just man, but the universe. Because this has been denied by those who have attempted to squash progress by the imposition of a mathematics which cannot account for negentropy, which cannot account for progress, which cannot account for reality. So in particular, LaRouche insists that, and this part is very explicit in his book, because the presentation we're going through tonight is the third chapter in So You Wish to Learn All About Economics, which is available on Amazon. But anyway, he makes very clear that the universe is negentropic. It's not just humanity, but life, the universe as a whole is negentropic. There is an unseen continuous reality behind the discrete reality that we see. In other words, we only see part of what is real. And the geometry of spiral and conical action is much closer to an accurate representation of that reality than algebra or mathematical Cartesian equations. In particular, you might notice that you often have mathematicians trying to come up with equations where one side is equal to the other side. Well, in negentropic universe, both sides don't always equal the same thing. If you're operating according to a negentropic principle, one side of your equation is not going to equal the other because you're transforming things. You can't measure your economy in bolts or tonnage of freight or tonnage of steel, whatever. You can't measure it in those ways. So LaRouche has developed other ways to measure. But anyway, I'm going back to this list. The third item is that real knowledge comes from unique experiment. It doesn't come from declarations such as the so-called laws of thermodynamics. And this third section of his class is very much a refutation of the laws of thermodynamics, in particular the second law of thermodynamics, which sort of applies to small machines and small things, that if you're got your bicycle turned upside down and you run the pedals and get your wheels going, they're going to eventually slow down. Yeah, well, so that does hold in the small, but it doesn't hold in the large, for the universe as a whole or civilization as a whole. So anyway, from experiment, we see that the central subject matter of economics is technology, technological progress. This is the thing which the British School of Economy and Mathematics cannot account for. So momentarily now, I'm going to turn it over to Tony Pappert, and he is going to review a couple things from last week. And then we're going to play the video of the third part of LaRouche's presentation, and then we'll come back and we'll discuss more about that. So go ahead, Tony.
I think I'll truncate what I was going to do. I was going to do a kind of recap of last week's class, because I know several people found it difficult. If you did, I'd like to ask you to review the tape, which is on our website, prometheanaction.com. But I have some pointers to help you in that review, so you could probably understand things that you didn't before. But Mike gave such a marvelous introduction to this tape that I'm thinking I'll skip that and introduce it later if there's time, because I think it will be a help to, it can be a help to people. But I don't want to, I mean, Mike gave a good introduction. I don't want to separate unduly the introduction from LaRouche's video. Let me just do one thing though, and also an introduction to the video. Another concept in this video, which Mike, I think, didn't reference, is energy flux density. And this is a fundamental principle of physical economy. And I just like to try to demonstrate that, because that's integral to the show you're about to see. I mean, energy flux density can be measured as energy flowing through a surface per unit time. But going back a step, I mean, the principle of energy flux density is essential to all work into civilization. I mean, you see the similar principle in the lever, one of the first tools, as everybody knows, that due to torque, a small force on the far end of the lever can produce a big force, on the end of the lever, which is close to the fulcrum. Same principle, I mean, again, in that sense, the same principle of a knife, that a small force on the handle of a knife produces a big force at the blade or at the point of the knife. So energy flux density, as I said, energy passing through a unit surface in a given amount of time, however you manage that, however you you denote that. Something very close to energy flux density, if you think of it, is temperature, operating temperature. And the man's progress in being able to produce hotter fires, of course, going back to Prometheus, who's in legend first gave us fires, man's progress in being able to produce hotter fires over the millennia is what has made possible the progress of metallurgy. And in fact, we could speak of a copper age when mankind was pretty much limited to use of copper for tools. And as we were able to achieve higher temperatures in our furnaces, we could go on to bronze, the Bronze Age, still higher by being able to work tin along with copper, still higher temperatures in the Iron Age. And actually, already in ancient times, people were able, in India at least, were able to produce the still higher temperatures required for steel. So, as I say, it's the increasing operating temperatures we were able to use in industry, which brought us from the Bronze Age to the Iron Age to the Steel Age to today. There was a tremendous article about this in EIR magazine in 1985 by a friend of mine, Bob Gallagher. And really, the crux of the article is summed up in this chart. How technology elevated the power of labor in blast furnaces, 1700 to 1974. So this really is really something. I mean, it shows these arcs of increasing of new technologies in iron making and steel making, right? And what are these arcs? The y-axis here that's going up through time is productivity, number of tons per operative per year. So that's here the y-axis. The x-axis is energy flux density, just as I was talking about, in million BTUs per meter squared per hour. Energy flow through a standard surface per unit time of an hour. And these successive arcs are actually different successive technologies. This one is charcoal. I mean, you have the iron ore in there, and you have a reducing element, which is some form of carbon. So the first form here was charcoal. And here, as you see it, is the charcoal blast furnace of George Washington's father in Virginia. So here's the arc for charcoal. Here's the arc for anthracite coal. And here then is the arc for coke, which is made from bituminous coal, but coke is a much better product for steel making than bituminous coal. So that's this arc where Andrew Carnegie pushed through successive revolutions in technology of steel making up through the Bessemer converter with huge, vastly increased energy flux density, speed and the speed of combustion, through forcing air or oxygen up through the Bessemer converter. Here, the arc of progress in World War II, and then post-World War II. So, that's an illustration. And many among our viewers I know are experienced engineers in all kinds of fields. So they probably have, much better examples. But this is a historical example of the rise of energy flux density correlated with productivity per man hour. So with that, let me pass it back to Mike.
Okay, so without further ado, we're going to attempt to play this video. Okay, here we go.
Be fruitful and multiply and replenish the earth and subdue it. During this program, travel deep into the innermost thoughts of the man whom Russia's rulers have said they fear the most. He is one of the most controversial international public figures of the decade, chief executive for an international news agency, and hated by powerful international financial circles for his 10-year campaign for international monetary reform. His fundamental discoveries in economic science have made him the world's most successful economic forecaster.
The following program is one of 5 parts of The Power of Labor, an educational special on economic science written by Democratic presidential candidate Lyndon LaRouche. The Power of Labor was produced for classroom use and is intended to be accompanied by Mr. LaRouche's textbook, So You Wish to Learn All About Economics.
Now we shall examine the meaning of negentropy in terms of economic science itself. By the term economic science, we mean that science as first developed by Gottfried Leibniz during the period 1671 through 1716. Economic science, strictly defined, is a branch of physical science. Leibniz's discoveries establishing economic science include his development of the proper scientific meaning of the terms work, power, and technology. Terms which Leibniz defined as an outcome of his mastery of the principles of design and function of heat-powered machinery. All machines involve 2 categorical principles of design and function. First, the motions essential to accomplishing work useful to humanity as a whole are studied. And these motions are incorporated into the design and design of use of a machine. This machine is then powered by human, animal, water power, wind power, or heat power effort. With the development of heat-powered machinery, the possibility was set into motion, in Leibniz's words, by which one man could perform the work of 100 others. Secondly, the most characteristic feature of machinery and similar processes in general is the transformation of the power supplied to the machine, or to an analogous process, to a relatively higher energy flux density. Energy flux density of applied power. This transformation of energy flux density is key to discovering the physical meaning of the term negentropy in economics. We shall now explain simply the meaning of the term energy flux density. Supply 1 ton of pressure to set a process into motion. Now measure that motion. Motion can be measured in the distance of displacement, or the cross-section area of displacement, or the volume of displacement. Wherever the term energy flux density is used, one must keep all 3 kinds of displacement in mind. However, we measure energy flux density in terms of the cross-sectional area of the displacement affected within a process, such as kilowatts per square meter. For example, if 1 ton of effort supplied to power a machine is originally at an energy flux density of 1 ton per square meter, and the machine applies this effort to its work through a cross-sectional area of effort of 1/1000th of a square meter, then disregarding the friction within the machine process, the work effort is applied at energy flux density of 1,000 tons per square meter. For reasons we will make clear as we proceed, we measure the work action of machinery and analogous processes with 2 successive degrees of refinement. In both of these degrees, the geometric definition of effort used is the following. Effort is measured in area. We define the physical meaning of area mathematically as the area enclosed by circular action. Instead of saying circle, we define a circle as the most elementary of the products of simple circular motion. Next slide. Given an area of effort, we measure the amount of effort by the number of rotations of circular action per second. For the case in which the area of effort is constant, the greater the rate at which the circular action rotates to generate that area, the greater the amount of effort. In other words, the greater the energy flux density. As you can see, in the mathematical measurement of the term energy we are describing here, it is the amount of circular action which is the measure of the effort being applied, the measure of energy. The faster the point moves around the circumference of the circle, the more energy is being applied to the area of the circle. Next slide. Therefore, if the speed at which the point moves around the circumference of a circle remains constant and the circle becomes larger, the number of rotations per second is less. On the other hand, as we make the area of the circle smaller, keeping the speed of the point constant, the number of rotations per second increases. These 3 slides give you an initial working definition of both energy and energy flux density. Before turning our attention back to Leibniz's conception of technology, let us make the definition of energy 1 iota more precise. Now we've expanded our discussion of the definitions of energy and energy flux density from 2 dimensions to 3 dimensions. Now, instead of seeing circles and circular action, we are seeing the cylinder whose end view is the circle. The end view of a spiral on the outer surface of a cylinder is the circumference of the circular cross-section of the cylinder. In this case, for reasons which will be clear a few minutes ahead, we have drawn on the cylinder what we call a self-similar spiral, a spiral in which each cycle of rotation is a geometrically similar figure to each and all of the preceding and following cycles of rotation. Now we see the cylindrical 3-dimensional image of increasing and decreasing speeds of movement of a point around the circumference of a circle. Next slide. Now we have drawn a time axis parallel to the cylinder. The arrow points in the direction of the clock's movement forward in time. This means that we are now measuring the distance between complete cycles of rotation of the spiral around the cylinder in cycles per second. We measure the wavelength of each complete cycle as the amount of distance light travels in that amount of time. Next, we observe the point moving along the spiral again. If we attempt to speed up the speed at which the point moves along the line, we must sooner or later reach the speed of light. If we attempt to go at faster speeds than light, we must either change the speed of light, which is a theoretical possibility in mathematical physics, or we must create what mathematical physicists call a singular condition in the physical phase space in which this attempt is being made. Let us avoid these advanced problems in physics and assume for the moment, for the present discussion, the speed of light is unchangeable. And let's assume that we can never go faster than the speed of light. In that case, at the speed of light, the only way in which we can increase the energy flux density of the self-similar spiral action is to increase the frequency of the rotation, which means that we must shorten the wavelength of each of the cycles of the cylindrical spiral. So, as we shorten the wavelength of the spiral, the point speeds up. As we make the cylinder narrower, the point speeds up and the wavelength changes in terms of cycles per second. As we make the cylinder thicker, the opposite effects occur. At the speed of light, we cannot increase the energy except by making the circular cross-section thicker. We cannot increase the energy flux density except by increasing the frequency. If we narrow the cylinder of spiral action, the frequency increases. the wavelength shortens. What we have described is based chiefly on what Leibniz calls the principle of least action. The importance of that principle for economic science appears in the following way. Imagine two heat-powered machines, each of which consumes the same amount of coal equivalent per hour. However, if these machines are used for the same kind of work, the same operator, using the first of the machines, produces more output per hour than with the second. The difference in quality of the two machines is a difference in organization of the machines. This is an illustration of the following general fact about machines and analogous devices and processes. The difference in quality of machines and analogous devices implies the existence of principles of organization of machine designs, such that improvement in organization signifies a greater increase in the productive powers of labor, greater relative to a constant level of supply of power to the machine. These principles constitute the meaning of the term technology. The measurement of technology is the principle of least action. This brings us to the matter of defining the term work. Although Leibniz's treatment of his principle of least action implies the correct definition of work, the required mathematical physics definition of work was not possible until the successive work of three 19th century German scientists, Carl Gauss and Gauss's immediate leading successors, Lejeune Dirichlet and most emphatically Bernard Riemann. As we've already outlined, the existence of society depends upon increase of the potential relative population density. Let us now measure potential relative population density mathematically by areas of circular action. This means that an increase in such potential corresponds to an increase of the area of a circle. This increase becomes now our proper, strict definition of the meaning of the word work. We must now examine what happens in between the transformation of the relatively smaller circle to the relatively larger. If the rate of increase of potential is constant, then the geometrical figure which describes such a process mathematically is a self-similar spiral on the outer surface of the cone. This is what a constant rate of increase of potential relative population density looks like mathematically. You should recognize that this is a special form of Leibniz's principle of least action. It is a higher form of that principle than the cylindrical version we described just before this. In other words, functions of cylindrical self-similar spiral action are functions of energy, while conical self-similar spiral functions are functions for measuring work. Next slide. By drawing a straight line down the side of the cone, from the apex of the cone to its base, the straight line so drawn cuts through the self-similar spiral at points which correspond to one complete rotation of the spiral around the cone. This figure shows the circular cross-sections of the cone at those points. These circles correspond mathematically to the increased potential relative population density at those points. Next slide. This time we have drawn the time axis in the same way we drew the time axis for the case of the cylindrical self-similar spiral. Observe that in half the time taken to go from one cycle to the next, the spiral has moved less than half the distance between the two circles along the central axis of the cone. The point which corresponds to half the time elapsed is called the geometric mean. The point which corresponds to half the distance along the central axis of the cone is called the arithmetic mean. Next slide. Now we have cut the volume of the cone between two of the circles. The plane cutting through this volume creates an ellipse. Observe where the two foci of the ellipse stand with respect to the arithmetic and geometric mean. This ellipse describes something which is mathematically characteristic of the process of increase of potential relative population density. Next slide. In order to show the significance of this elliptical cross-section of the volume between the two circles, we have cut the volumes between the two foci of the first ellipse with the second ellipse. We mean to indicate that we continue to cut smaller and smaller volumes within this cone in the same way, either indefinitely or until we have some reason to say we have reached a limit. This cutting process is the basis for a general theory of elliptical functions. The successive cutting of smaller and smaller subdivisions of the volume of one cycle of the spiral's rotation is what we call an iterative process. In the foregoing case, we said cut the volumes between the two foci of each ellipse. We might have defined the rule for successive subdivisions in some other way. For our purpose of illustration here, we chose to subdivide the volume between the foci of the ellipses merely because that is the simplest illustration available for classroom purposes here. Next.
So I want to stop it there and say that this minimum principle of action is the human mind, the human individual person's action upon the physical economy. And we're dealing here with a linear expansion of potential relative population. But really what we want to create is a horn of expansion of the type that you see on a brass horn or a brass instrument, where you have the rapid hyperbolic expansion out to emit the sound from the instrument. But anyway, let's go back here.
Next slide. Let us assume that there is a lower limit beyond which we must no longer subdivide the volume of the cone by elliptical cross sections. As Riemann and others have shown, there is such a limit. In fact, that limit is the basis for Leibniz's rejection of the argument that the interval of some physical action could be infinitely subdivided. The principle that there is a limit for subdivision of intervals of physical action is one of the fundamental differences between the calculus which Leibniz published in 1676 and the different sort of calculus which Newton published approximately 10 years later, and is also the difference between Leibniz's calculus and the version taught in many calculus courses today. The figure on the screen shows the mathematical significance of such a Leibniz-Riemann lower limit of subdivision in terms of functions of a complex variable. Whatever that next ellipse is, which we are forbidden to construct, that forbidden ellipse represents some volume between the two circles, as we've illustrated that by the figure now showing on the screen. This smallest volume between the two circles has some definite height, as measured along the central axis of the cone. It also corresponds to some definite length of the spiral on the outer surface of the cone. It also corresponds to an interval of time. It also corresponds to some small wavelength of electromagnetic radiation at the speed of light. This small interval of action defines what is called the singularity of the conic self-similar spiral action for the increase of the potential relative population density between those two circles. Imagine that a cylinder is constructed as an extension of any of the circles generated by the self-similar conic spiral function. This would correspond mathematically to the propagation of energy in the same form as an ideal laser beam. If that ideal laser beam reached an appropriate form of obstacle, the result would be a conical function in which the apex of the cone would lie in the future, and the largest circles of the cone in the present and the past. In this way, a singularity or singularities would be created by the impact of the ideal laser beam with that obstacle, and it would then appear that the energy of the ideal laser beam had been converted into work. For comparison, let us apply what we have just shown about conical functions to the case of self-similar cylindric functions. The most obvious of the mathematical differences between cylindric and conic forms of self-similar spiral action is that in the cylindric form, as shown here, the geometric and arithmetic means coincide. Next slide. The iterative subdivision of the volume of one cycle of a conical spiral, leading to the indivisible residue, does not occur in the case of the cylindric spiral, as we see on this next slide. Now imagine energy radiated in a coherent, laser-like mode over some distance. It encounters a barrier. This barrier must be an object, or it might be a limit, such as the speed of sound or the speed of light. Bernard Riemann examined such a case for the propagation of sound waves up to and past the speed of sound. At this barrier, the cylindric self-similar spiral shrinks into a conical tip and vanishes. In the case of sound waves, in Riemann's 1859 thesis on the propagation of plane air waves of finite magnitude, driving the speed of propagation of sound waves up to and beyond the speed of sound generates a shock front.
If you look at this model, you will see that you have a waveform at the top, but you see that the wave is building up to a single crest, like you see at the ocean when waves hit the beach and start to create breakers.
Ignoring what occurs as we attempt to exceed the speed of light, let us look more closely at what occurs in the case of acoustical shock waves and applying radiated energy against a physical barrier. Next slide. Here we see what we might view as the destruction of energy in producing work or in converting energy into work. Next slide. Remember that energy is generated by work. Next slide. Now energy is converted into work. It should be obvious to us that what we must compare is to compare the work required to generate energy with the work accomplished by using up the energy generated. We must measure the work in both cases in units of increase of potential relative population density. Looking at the next slide may help to make the point clearer. Imagine a flat piece of paper or a motion picture screen hanging behind a side view of a cylindrical, self-similar spiral form of action. On the screen, we see a sine wave, like the image of ordinary house current on the screen of an oscilloscope. This is the general form of all coherent electromagnetic radiation, including perfect laser radiation. This is the geometric image of energy in a two-dimensional framework. If energy is transmitted in the form of a light wave of this form, the amount of work accomplished by the light wave on meeting a barrier is measured in a smallest unit, called a photon. This amount of work corresponds to the singularity of the conical work function occurring as we attempt to convert the light ray into work. Ordinary light waves are about 1/10,000th to slightly larger than 1/1,000,000th of a centimeter long in wavelength. Imagine that the frequency is increased. So there are about 800 million waves packed in the distance of the wavelength of visible red light. This is a cosmic ray. How much energy does a cosmic ray represent in comparison to a ray of red light? Yet these cosmic rays have wavelengths much greater than the radius of the electron. These illustrations indicate the mathematical meaning of the terms energy, work, and technology in the more advanced sense made possible by the successive work of Gauss, Dirichlet, and Riemann, and others during the 19th century. My own discovery in economic science was chiefly to recognize that the definitions of work and energy, as they occur in Riemann's mathematical physics, must equate the value of work to an increase of the potential relative population density. By making this discovery and elaborating the significance of that discovery over the years since 1952, my collaborators and I have returned to economic science, the standpoint of Leibniz, to recognizing that economic science is a branch of physical science and is in fact the most important facet of physical science in general. This seems to be a very large statement. Therefore, let us examine the way in which Leibniz defined the terms power, work, and technology. Leibniz defined work in terms of the physical output of the operator of a heat-powered machine. He defined technology as those principles of organization and design of machines which enable us to apply power to increase the rate of output of the operator. In general, that definition of work was the definition used by Leibniz and his followers in mathematical physics. That definition of work, based on the evidence of economic science, is the proper basis for defining the terms power, work, and technology in physics. Therefore, if we refine the definition of work, as I have done beginning 1952, we must also change the definition of work employed in mathematical physics generally. No term in physics can mean anything other than it means in its original definition. Physical science is, after all, nothing but the study of the laws of the universe. We study those laws in terms of human practice. By improved knowledge of the laws of the universe, we increase man's power to command the universe, as the instruction of Genesis commands us to do. As we are able to increase mankind's power to survive and live per person through use of improved knowledge, we prove that those improvements in knowledge have practical validity for man's practice. Therefore, the only valid experimental proof of the accomplishments of fundamental scientific investigations is proof based on showing that the application of those principles to the organization of human economic practice, by which we must mean physical economy of a society's practice, yields an increase of the potential relative population density of entire societies. That is the meaning of the role of economic science within the body of physical science as a whole.
Okay. So let me share something else with you here. So I gotta do one more thing first. Just a second. Okay. Okay, here we go. All right, so you can see that. Can everyone see that chart?
Yes.
Okay. All right, so this is a chart of population growth projected out to sometime in the future. But you see it has that hyperbolic aspect to it. And if you think about the moon, for example, right now, we have the technology where we could maybe support 3 or 4 people on the surface of the moon, on an ongoing basis. But we need to develop the technologies that we could have 100 people on the moon, or several thousand, or 1 million people on the moon. And that requires technologies which we do not yet have. So this is the point of Mr. LaRouche's concept here, that the potential relative population density reflects the interventions of individual people in making new technologies available. So I wanted to discuss that with you. I also wanted to discuss this electromagnetic spectrum a little bit, because he was talking about, you remember in 1984, he was in the middle of working with the people in the Reagan administration around what President Reagan had adopted of his Strategic Defense Initiative policy. So we spent a lot of time educating people about the electromagnetic spectrum and so forth. But in particular, you see here the change in magnitude between the size of radio waves, which can have wavelengths the size of buildings, down to the size of a honeybee. And then when you get into the ultraviolet, the X-ray, and the gamma rays, you're dealing with wavelengths that are in the frequencies corresponding to the size of molecules, atoms, and atomic nuclei. So this is the issue of changing the wavelength that he was discussing earlier. And I also want to show you something else here. This is a Crookes radiometer invented by Sir William Crookes in 1873. That was back when Thomas Edison and other people were working on bulbs of all kinds. But anyway, this is a semi-evacuated bulb with a pin in the middle and a sort of a pinwheel attached on top. And when it is placed in the sunlight, or in light coming from any source of light, the black sides of the paddles, I guess we can call them paddles, the black sides absorb some of the energy that's transmitted and turn it into heat. And that heat is applied to some of the air molecules which are still in there. This is not a fully evacuated bulb, but semi-evacuated bulb. It won't work if you have a completely vacuum environment there. But anyway, that's what turns this radiometer. Here's a better shot of it. So I wanted to show you these to get a flavor of what he's talking about, because you have work being done on the sun or in a light bulb. The work is transformed into energy, into light energy. The light energy hits the black paddle, is converted into work by heating up the black paddle. The black paddle heats up the what exists of an atmosphere in there and causes the rotation that you see here. So these are some of the things I wanted to show you to bring a little bit more life to some of these questions. Let's see here. Oh, yes, I got to break out of this. Okay, let me go here. All right, so I wanted to mention a couple other things, because as I say, we're intent on not just expanding the cone in a linear fashion, but having a nonlinear hyperbolic expansion. And there are many things going on right now that portend the opportunities if we are able to implement the election of President Trump and the election of a suitable Congress to allow us to make further advances in the development of the country. But some of the things that are going on right now is that in the next few weeks, we're going to have the fourth test flight of the Starship super heavy combination. The Boeing Starliner is the first flight with people to the International Space Station, will take place in a couple of weeks. The Dream Chaser, which is sort of a mini space shuttle flyback system, reusable flyback system that's designed to take, for the moment, to take cargo, but eventually take people up into Earth orbit, will undergo its first flight probably in May or June. And also this year, we expect to see the first flight of the New Glenn fully reusable rocket system, which has been developed by Blue Origin. Those are a couple of things. There's also robots are now being, not just arm robots, but humanoid robots are now being tested in automobile plants in China and the United States by multiple companies who are developing this technology. There's Helion Fusion Company from Washington State expects to produce net electricity in their machine that they are building at the moment. So there are many things of that nature that are ongoing, which portend the potentials which we have, but we have to actualize those potentials. So those are my comments. Do you have any further comments, Tony?
No, I don't think so at this point, and not that I know of. Probably we should open up to discussion.